In this page, I'm going to discuss the second law efficiency. Um, we have learned about the first law efficiency, which we call as the thermal efficiency for heat engine, and the coefficient of performance or COP for the refrigerator or heat pump. And now, either for thermal efficiency or COP, the first law efficiency is defined as the ratio of the desired output compared to the required input. Okay? And that definition is based on the first law of thermodynamics, and that is why we call that as the first law efficiency. This first law efficiency is really beneficial for us to estimate or the evaluate the performance of the cycles like heat engines or refrigerators. But essentially, it gives us the information of how much fraction of the input is utilized as an output. But it does not give us any information about whether or not that the heat engine or the thermodynamic cycle of that efficiency is possible or impossible. Now, in the previous part, we discussed the Carnot cycle efficiency. And the Carnot cycle efficiency is the maximum possible efficiency that we can achieve. Okay? If I draw, kind of efficiency, okay, then there must be a certain maximum point, which is Carnot efficiency, and no heat engines or no refrigerators or no heat pumps can exceed that limit. Okay, so if someone else claimed that their efficiency is higher than the Carnot efficiency, like there, that is not possible. But only with the first law efficiency, we cannot tell whether or not this device is possibly, manufacturable. Now, in order to overcome that limit, now we define a second law efficiency, and this second law efficiency is defined as the ratio of the actual efficiency to the maximum possible thermal efficiency, which is the efficiency of the Carnot cycle. So if we express that second law efficiency in terms of equation, then the second law efficiency, in order to distinguish this efficiency from the first law efficiency, we put the subscript 2 in Roman number as a subscript. And now this second law efficiency is defined as the efficiency of the actual system to the Carnot efficiency. Or if your thermodynamic cycle is a refrigerator or heat pump, your second law efficiency is defined as the COP of real actual device compared to the COP of the Carnot cycle. Now, why is the second law efficiency beneficial to us? Let's try to compare these two cases. So one heat engine, okay, let's say that engine A, runs under the heat source of 600 Kelvin and now sink at 300 Kelvin. And this engine gives us the thermal efficiency of 30%. Okay. Now, let's think about another engine, like engine B. This engine operates at source of 1000 Kelvin and heat sink of 300 Kelvin. And this engine also gives us the first law efficiency of 30%. Now, based on those given conditions, which one is better? Can you tell which engine is better in terms of efficiency? Now, obviously, if we look at only the first law efficiency, both engines are the same. So we can deceived by this number saying that, yeah, okay, so engine A, engine B, should be the same because they give us the same efficiency. But is that really true? Now, let's try to calculate the Carnot efficiency or the second law efficiency for engine A. So let's say that engine A, okay? So then this is the thermal efficiency divided by the Carnot efficiency. Okay. Now from the given source temperature and sink temperature, your Carnot efficiency, reversible, is 1 minus 300 over 600, which is 50%. Okay. Now that gives us 30% divided by 50%. So the second law efficiency of engine A is 0.8 or 80%. Now how about the second law efficiency for engine B? We have 30%, okay? And from the given heat source and sink temperatures, your Carnot efficiency of engine B gives us 1 minus 300 over 700, that is that is 300,000, so that is 7%. So now we have 30% divided by 70%, that gives us 0.43 or 43%. So now, even though we cannot tell the difference between engine A and engine B if we only have the first law efficiency at 30%, now by having the second law efficiency, can you tell me which heat engine is better? Of course, engine A is better because that gets to almost 80% of the ideal efficiency. But now let's rephrase this question. So now you have certain money. Then you want to invest your money to improve the performance of these two engines. Now, from this, between this engine A and engine B, which one do you want to invest your money for the improvement? A or B? My answer is B, because now it only has 43% of the maximum efficiency. In other words, we have much more room for improvement. So if I invest the money that I have to engine B, then I think I can expect more improvement in terms of the performance of engine B. Engine A only has slight room, and it's really hard to have certain improvement because it is already very close to the ideal condition.